So hello everybody. So my name is Mohammed Hussein Hamadi. Today I will talk about my work done under the title of Experimental Investigation of Turbulent Counter-Rotating Taylor Couette Flow in very wide gaps for eta equal 0.1. So first, to have a general look about our experimental setup here, we have an experimental setup with an outer cylinder of 7 centimeters and inner cylinder of 7 millimeters. So by that we have a radius ratio of 0.1 and a gap width of 63 millimeters. Also, we have in our experimental setup an aspect ratio of 11.1. The driving parameters that control the flow inside the gap are the Reynolds, shear Reynolds number, and the rotation rate. So first we start by doing flow visualization. By that we seed the fluid with the kaleidoscope particles, and then we produce a vertical laser sheet so that allows us to capture the flow in the axial radial direction. So the figure at the right we are showing the stable Taylor vortices. At the left we are showing like a picture of the TC experiment with visualization setup. So for the visualization setup, here we are showing the results for low Reynolds number. So the first image are shown for mu equal minus 0.01, just to verify this. So imagine that the inner cylinder is rotating with 100 RPM, the outer cylinder is counter-rotating with minus 1 RPM. And by that we can observe like a stable Taylor vortices. But as we know, in viscous fluid, the secondary flow induced by the Taylor vortices can extend the neutral surface, which is the place where the azimuthal velocity vanishes. So here for mu equal minus 0.043, can observe how this neutral surface detaches from the outer cylinder wall. And as we increase more the counter rotation, we can observe how this neutral surface detaches more and more. Then we increase more the counter rotations, and we observe this kind of oscillating patterns. It's kind of elongated Taylor vortices that oscillates around the inner cylinder. Then to measure the velocity field inside the gap, we use PIV, and especially we use a fast speed PIV method, PIV measurements. So by that we use phantom camera 640, which allow us to have 200 frames per second. So the camera was placed above our apparatus, taking the benefit of the transparent top plate, so we can capture the fluid inside the gap. So also the laser was placed behind the apparatus, so it generates a horizontal laser sheet. So by that we can capture the azimuthal and radial velocity component. The figure at the left show the flow field that can captured by our setup here. And also we should mention that the position of the laser is not fixed, so we can lift it up and down. So by that we did measurements in different heights, and then we average this to calculate our average velocity field. So for here we are showing the azimuthal velocity field for Reynolds equal 20K. So in this presentation I'm showing the results for Reynolds equal 20K for different rotation rates or different mu. We can observe here, as we see in the visualization, that the velocity for counter rotation decrease from positive values of azimuthal velocity to negative ones. So it passes through 0, where it's the radial position of the neutral surface. The figure at the right, I'm showing the position of this neutral surface as a function of mu. We can observe that for co-rotation, mostly the neutral surface is on the outer cylinder, it didn't detaches yet from the outer cylinder. For very low counter rotation, it starts detaching, and for high counter rotation, it detaches more and more. And here we are showing in the figure two theoretical predictions. The one in red is the one for Chandrasekhar, for inviscous flows, which have a very good agreement with our result for high counter rotations. But for low counter rotations, our result detaches from this curve, and it's between the two predictions of Eger-Grisman and Chandrasekhar, which means that we have kind of patterns, but it is not this result pattern that Eger and Grisman predict it. Then the angular velocity was also studied here. Here we can observe that the counter-rotating profiles are in very good agreement with the laminar Couette solution, but what you can observe also that for low counter-rotating profile, we have a very small angular gradient in the bulk. To focus more on this, we plot here the average angular velocity for the three low counter-rotations, and we plot the normalized radial gradient of the angular velocity as function of mu. You can observe that for very low counter rotation, this gradient achieved the minimum. And this results are in very good agreement with the one done for eta 0.5 and eta 0.375 done by Freudsheim. And here, this result coincides with the appearance of the Taylor vortices, and in the previous work done by Freudsheim, also this results coincide with the maximum transport of angular momentum. Finally, we studied the angular momentum profile. It shows mostly the same result with the angular velocity. So we have for co-rotating, it follows the Couette solution, and for counter rotation, it's mostly we have mostly no gradient in the bulk, but in the outer near the outer boundary layer, the curve deviate downward. So as a summary, we can obtain the different pattern in the very wide Taylor Couette flow. Also, we observe that the radial position of the neutral cell detaches from the outer cylinder for counter rotation, and we observe that the angular velocity achieves a very small gradient in the bulk and low counter in the bulk. The same as the angular momentum. As an outlook for the future work, we are willing to, we already did PIV measurements for different Reynolds, for higher Reynolds, and we want to analyze more the flow field we have in details and study the energy distribution between turbulent energy and the contribution of turbulent flow and the large scale patterns and energy, and study the angular momentum transport and compare the angular momentum transport calculated by PIV measurement with the one done with the direct torque measurement. Thank you. So if there is any question.
All right. Thank you very much, Mohammed, for your presentation. Yeah, as before, feel free to unmute yourself and speak up if you have any question, comments. No? No?
Could I see the neutral surface detaching again? How it detaches from the cylinder, the neutral surface?
Yes, the neutral surface, like for counter rotation, it starts detaching from the outer cylinder, and for higher counter rotation, it detaches more and more from the outer cylinder.
Mm-hmm. Okay.
So I have a question on the resolution that you get with your PFV. So you have this 4 megapixel camera, right? So what is the, let's say, the scale that you can resolve in your PFV as compared to, let's say, the Kolmogorov length scale?
We have like, it's 0.08 millimeter per pixel.
0.080 micrometers.
Yeah.
And how does that compare with your Kolmogorov length scale?
I didn't compare yet with this.
Sorry?
I didn't compare, like I didn't did comparison yet.
Ah, okay. Thanks for the answer.
But maybe I can interfere. Hi, it's Sebastian here. So it's much larger, especially at the inner cylinder, because the inner cylinder is only 7 millimeters thick. The boundary layer at the inner cylinder is so thin that it's really very hard to resolve it. I mean, it's just it's the same experiment, the same apparatus as you have measured for the ETA 0.5 with us campaign, but now we have only a 7 millimeter radius cylinder inside. So basically just a very thin shaft. And also we wanted to measure the torque inside the system, but unfortunately we found a new, more precise or more sensitive torque sensor for it, but still the measurements are not that reliable that we wanted to show it. Okay. And otherwise we did everything into the inner torque, but this was not possible with the data we had from these measurements.
Mohammed, could you comment on the size of the vortices? They seemed, I was surprised at how small they are in the axial extent.
Yeah, the size of the vortex mostly for low counter rotation, they fulfill the whole gap, which is we have like a size of 63 millimeters. So we have a circular vortex of 63 millimeters. This for low Reynolds, but for higher Reynolds, using the PIV, we observed that these vortices are mostly elongated. So in width, they are much larger than compared to the length.
Thank you.
Welcome.
All right. Meanwhile, while we can continue with the questions, Fatma, can you please already start sharing your screen? Are there more questions to Mohammed? No? Maybe one last one from my side, which goes a bit in the direction what also Laurette already asked. You presented here the results for ETA 0.1. What happens if you go to slightly even smaller or slightly bigger radius ratio? How much does this kind of effect of radial positioning for the detachment is changing with the radius ratio?
Like for larger, like for 0.5, it mostly, I mentioned that it's a very good agreement with work done with Freudzheim for ETA 0.5 and the one of ETA 0.375. So mostly for counter rotation, the detaching for ETA 0.5, the detachment start for minus 0.2.
Okay.
For but in our case, this detachment start for 0.06. So for very, very low counter rotation, this detachment start.
And if you would even go to lower ones, then you come in the resolution program, what also Sebastian mentioned already with the sensors that you need. All right. Okay. So any further questions? No? Okay, then thanks, Mohammed, again. And then we can continue with the next talk. So now we will hear from Fatma Yahi, something about laminar turbulent transition in Couette-Taylor quad flow. So please go ahead. Fatma? Whenever you want, you can start.
Fatma, you must unmute yourself. Fatma?
We can't hear. Fatma, we can't hear you. No?
Can we unmute her?
It's okay.
No.
Okay.
Good afternoon. I'm Fatma Yahi from Mohammed Bouguera University from Algeria. My work is about differential heating effect of the outer cone on the laminar turbulent transition in the conical Taylor quad flow. I start with I start by motivation, main problem and modeling, and I discussed the results and finished with a conclusion. The study of the laminar turbulent transition in the conical Taylor-Couette flow system was motivated by the interest for differential industrial application like food product, jams and bechamel, and the mixing process. The principal motivation is the effect of differential heating on the appearance of different instabilities in the conical Taylor-Couette flow. For that, we have used an incompressible viscous flow contained in the gap between two coaxial cones and characterized by constant physical properties, density and kinematic. The inner cone is rotating with an angular velocity omega, and the outer one is maintained fixed. The flow is governed by the Navier-Stokes equations and the energy equation. The contra-dimensionless parameter used in this investigation are Taylor number, Reynolds number, and Grashof. By using the finite volume method, the equation system were integrated numerically. A second order upwind sham is used to interpolate the phase value of the various quantities from the cell center values for the convection term in equation. The temporal discretization is used. Excuse me. The temporal discretization involves integrating all the terms in the differential equation with time step delta t, and the integration of the transit term is implicit by using the second order. The simple algorithm is used to link pressure and velocity. The present figure presents the mesh grid geometry, and we discuss the result. We start by the case without differential heating. The basic flow is always laminar three-dimensional. For Taylor between L and 20, we observe the installation of the Ekman vortices just near the upper part, while the second is merged with the large cell extended along the annular space. This observation is consistent with the description of Manfred Mimmer in 1995 and the experimental results obtained in the case of the same annular space. At Taylor equal 45, we observe the installation of the Taylor vortices, which is stationary, and when we compare it with the experimental value, we obtain 6.8% we compare between the numerical and the experimental result. It's at 6 to 8%. Here we present the installation of the cells on the Taylor on the conical Taylor-Couette flow. Here it's the Ekman vortices and the formation of the first cell in which is in the large loop in the gap space. Here we present the contour and the profile of the axial velocity corresponding to the appearance of vortex flow. This figure presents the radial velocity in the gap and the contour, the profile of velocity in the same position at outflows and in the cell center and in the inflow. And the last figure presents the contour profile and dynamical pressure in the space. The downward helical motion or spiral mode appears at Taylor equal 48. This value is very close to the obtained experimentally in a small annular gap configuration, 47, with a difference of 2.12%. Here we present the succession of the generation of the cells, the spiral cells, and here we have a loop for the spiral mode. In this figure, we present the pressure, the dynamical pressure in different Taylor values. In the case of with the differential heating, the differential heating doesn't have the effect on the appearance and the structure of the Ekman and Taylor vortices. We have here we present different figures for various values of Grashof number. We observe that there isn't an effect on the Ekman cells and the Taylor vortices. But when but when the Taylor number decrease, we observe at the spiral mode, we observe the effect of differential heating on the structure of the cells, where cells length. At Grashof, higher number of Grashof, we observe that the cells emerge with the first one and becomes very large, comparing with the case, the dynamical case, Grashof equal 0. In this figure, we present the temperature profile for various Grashof number in the axial and radial direction for Taylor minus 52 and Taylor equal 52. In conclusion, it is not that the Ekman vortex, which appear near the upper part of the flow system, is characterized by size 4 millimeter, while the rest of the flow forms a large loop with size 141 millimeters. Only the first cell is stationary. It appears at the upper part of the conical Taylor flow. Cells are generated progressively relative to the equatorial plane and inclined relatively to the equatorial plane. It is also found that the results are in good agreement with the experiments. There is no effect on the Ekman and Taylor vortices with the presence of the differential heating, and the differential heating affects the vortices length in the spiral mode. Thank you for your attention.
All right, thank you very much, Fatma, for your talk. Yeah, questions? Feel up to unmute yourself and speak up.
Please.
No? Some questions?
Yes, there seems to be a question
Yeah.
over here.
Yeah.
Please ask your question.
Please. Just
Yes,
unmute.
yes. I have a question, please.
Sure.
Please,
Yeah, just speak up.
may I ask the question?
Yes, ask. Sure.
Please, what fluid do you investigate? What Prandtl number of this fluid?
The Prandtl number is about 7.
Ah, yes, okay. It is what?
It's a small number.
Okay, okay. Thank you very much.
Not at all.
I'd like to ask about the spiral vortices. Do those appear without the differential heating or only with the differential heating?
Excuse me?
The spiral vortices,
Yes.
do those occur when there is no differential heating?
Yes, it's appear. It's appear without differential heating. We observe the spiral mode with and without differential heating, but the length of the cells it becomes very large with presence of the differential heating.
Thank you.
Any other questions?
Perhaps I have a small one. So in one of your first slides, you found the critical Taylor number.
Yes.
And you said it was a 6.8% different.
Different between experimental and numerical.
Yes, indeed. But is that due to the scanning, let's say, of the simulations? Did you really try? I mean, did you also try 44 and 43 and 42? I mean, how many simulations did you do?
We have take 5 situations, but I don't. We have chosen the situation where we obtain the profile of the velocity, the radial and axial velocity, which is the same, which are obtained by the analytical calculation.
Okay, thanks.
All right. Meanwhile, Sebastian, can you already start sharing your screen for the next talk?
Unfortunately,
yeah.
It's blocked. Can you free it for Hamida?
Okay. Maybe one last question to Fatma. You said that with increasing the differential heating, you observed different number of vortices. But as you know from the basic system, you can also have vortex cells with different wave numbers, axial lengths, parallel existing. Did you also observe this kind of different states without differential heating?
Excuse me, can you repeat the questions?
You said with differential heating, you found these Taylor vortices with different wavelengths, so different numbers of vortex cells inside, basically. Yes. Right? The picture what you showed. But did you also found these states without differential heating? Because in the classical system, you can also have different kind of Taylor vortex flows with different wave numbers coexisting.
Yes, there are coexistence of different wave states.
Okay.
But the calculation it's take I can't find the word.
Okay, it's fine. Thank you very much.
Okay, thank you.
Okay, then
Thank
we
you.
continue with the next talk. So next talk will be given by Sebastian Merbold, and he will tell us about turbulent flow structures in centrifugal stable Taylor flow. So please, Sebastian, go ahead.
Yeah, thank you for the introduction. So we already have learned about the eta 0.1 case by Mohamed Hussein in the two talks before. And now I want to present measurements in the same experimental setup with the same geometrical configuration, but in the Rayleigh stable regime. And so our Taylor-Couette system is classical Taylor-Couette system. We have a gap width D, a radius ratio eta, and an aspect ratio of gamma. And we use the ratio of angular velocity to define our dynamics. So it's omega 2 by omega 1. We also use the de Broglie shear Reynolds number, which Mark has already shown in the first talk today. And as we have a very, very small inner cylinder, for us, it's also an important factor to look for this lambda, which is the ratio of the angular momentum. And it is, if it's larger 1, the system is stable. So this is classical thing for all the systems, but due to the point that for eta 0.1, this is the case for eta, so it's really stable if lambda is, sorry, if mu is larger than eta squared, which would be 0.01. So we use now lambda as an indicator to show our stability of the system. Of course, there is the angular momentum flux, J omega, and I will use this part also later where I present our UR omega measurements from the PIV. And from this, one could derive the quasi-Nusselt numbers. And in the past, we have done a lot of experiments with eta 0.5 and 357. But now we want to go to this limit with only this, like a pencil inside the system. And as I showed, or as Mohamed Hussein has already shown, so he has shown everything what is happening left to this Rayleigh line, where lambda equals 1, and now there's the second line of the solid body rotation, where mu equals 1 and lambda is 100, and everything in between one could name the quasi-Keplerian ratio. And I want to show you results very close to the Rayleigh stable line. So lambda equals very close to 1, but it's larger than 1, up to 2. Yeah. So experiments done in this regime. And first of all, we of course did flow visualization, and I hope you can see some parts of the video. So this is the entire system, and normally you would expect that the system is stable, and you would see only a Couette solution and no instabilities. Of course, one usually sees for these flows that from the end plates, some effects are playing a crucial role, and then from there you have a growing structure which goes into the system. But what we see here is, for this eta 0.1, that we have structures in the central part of the system, around the mid-gap, and not at the end plates. If we change the parameter, and we go closer to closer to the Rayleigh line, of course the instabilities become more dominant. And now you can see in the flow visualization that some structures are hitting the outer cylinder wall. So we can see here only a few millimeters at the outer cylinder wall. And if we even go further, you can see for lambda equals 1.02 that nearly the whole domain is already kind of turbulent and has a lot of structures. Where in, for example, similar cases for eta 0.5 or 357, you would only see some Ekman layers from the top and bottom plate, and in the central you would see just a gray laminar flow. So if we look into the system, we have now a light sheet sketch where left is the inner cylinder, right is the outer cylinder, and we can see how from the inner cylinder some vertical structures are detaching and moving towards the outer cylinder, and this is in the central part. And you can see this kind of structures again and again, and they happen arbitrarily over the height. So what we did then is to do the same PIV setup as Mohammed Hussein has presented for the other cases. So we put inside our Taylor-Couette system, we implement our laser. We use a high-speed PIV system for these cases. We look from above through our transparent top plate. And so by this, we see the azimuthal radial light sheet, and we can compute the data. So these are some figures from precessing measurements. So this is done by Freuzheim for the eta 0.5 case. And later we did also some measurements together with the Twente group in Twente. And then also we did measurements in 357. And now we go to the next stage with the 0.1. And if we look to the profiles, here we see for Reynolds number of 5,000 and lambda equals 1.1, we see our velocity profiles where the color code is just representing different heights of the system. And we are very close to the Couette solution, but we have, of course, a deflection from the Couette solution. And we do have a mean radial velocities over the heights. And we do see also fluctuations of the azimuthal velocity and of the radial velocity very strongly. And if we go to a higher Reynolds number, 61,000, but here in our lambda is 2, we can see that the profile at the inner part of the gap is more and more overlapping with each other, while at the outer part, we still have some difference over the height. And now we can, as we have a time resolved PIV, we can look a little bit more into detail. And what we are looking now at are the radial velocity fluctuations. So this is UR prime for the first case, Reynolds shear 5,000. And here I picked two heights, -5 millimeters and -45 millimeters, where you can see that from top to bottom, we go from a position very close to the inner cylinder to a position very close to the outer cylinder. And around here we have the mid-gap position. And so we have radial positions from top to bottom. And we have the azimuthal direction plotted over here and the time in this direction. So we have this space-time plots where we can see that these structures are detaching from the inner cylinder and moving towards the outer cylinder. And this we can see for many different cases. And if we plot UR omega, the shear, we can see that this is affecting very strongly also the shear of the whole system. And by this also we have a transport of the angular momentum. If we go to the high Reynolds number, we now see a very more situated structure at the inner cylinder where we have a lot of strong fluctuations which are moving downwards the azimuthal direction. And as you can see, some of these structures are living only shortly and don't survive over the entire gap, but some of these structures do survive over a long time inside the gap. And of course, by this, they transport the angular momentum, which is basically then represented also again in the shear UR omega, where of course this is a very strong behavior, very positive and negative shear at a location close to the inner cylinder. And then while we pass towards the central part and into the bulk, you can see that still there are these kind of structures, these kind of spiral kind of structures which moves through the system. And so as a conclusion, we can say we have observed an instability in the Rayleigh stable flow, but this one is formed at the inner cylinder and not formed at the end plates. The structures which then move towards the outer cylinder are strongly elongated in the azimuthal direction. This you can see already in the movie in the light sheet, because you can see the structure, although the fluid velocity is perpendicular to the light sheet, you can observe these structures which are very small in R and Z very long for a very long time. And these structures move through the entire gap. And what we can see, especially when we increase lambda, that these structures start to be only occurring at the central part of the system, and the end plates to stabilize the flow. So in this case, it's not something which is directly driven by the end plates. It's coming from the flow between the two cylinders. The structures have a spiral form, and we can see that the structures do transport the angular momentum from the UR omega. Only this transport quantity has, in terms of the Nusselt number, a size of about 20 to 30. What they contribute to the overall transport. Unfortunately, our torque measurements for this eta 0.1 weren't really reliable because it's only a 7 millimeters cylinder, which rotates still fast, but due to the small surface, the real torque acting to the inner cylinder is very low. And even with the most sensitive sensor we could find, the measurements do show some behavior, and we can see something, but we don't rely at the moment on all the data. That's why we omitted this in the presentations today. Yeah, and with this, I want to thank you for your attention.
All right, thank you very much, Sebastian, for a very nice talk. Questions? You can either speak up, raise your hand, or write in the chat, whatever you prefer.
Let me start.
Okay.
Sebastian, thanks for the talk. I have a question. So once you go thinner and thinner inner cylinders, do you also get into issues with, let's say, so when you spin it, let's say fast, the inner cylinder, does it become like unstable, like and the smoothness of the inner cylinder and things like that, the alignment of the cylinders and things like that? Yeah,
the alignment of the inner cylinder is always an issue for all the gaps. Yes, of course. We have more the trouble. I mean, the system for 7 millimeter radius or 40 millimeters diameter with the 700 meter length, this is still doable. That the cylinder doesn't start to bend strongly. But also, like after half a year running the system, the cylinder can. I mean, something can occur that the cylinder itself gets a little bit bended, and then we have to dump it and take another inner cylinder. That's a little bit a very big problem of it, but to align it with the rotation axis, it's the same problem as for other radius ratios, because usually also we use the same cylinder or the same shaft for the other radius ratios.
Okay, yeah. I can imagine that you can even get some modes in the axial or that it can vibrate kind of with some modes and things like that once it becomes really thin.
Yes, that's one has to really look that this doesn't happen. That's really an issue, of course. At some point it could start to have some oscillation, but we are very carefully not having this case.
Yeah, nice. Thanks.
All right. Any further questions? Meanwhile, Siad, can you already please start showing your presentation? Otherwise, maybe I have a very simple question. I mean, you showed these nice outward moving structures, but what, maybe you said it, but and I did not get it, sorry for that. What is the size of these structures, the dimension? Can you identify kind of a core of this kind of spiral structures are moving outwards? Or in comparison, let's say, to the dimension of this cylinder?
Yeah, so the dimension of the structures is smaller than the inner cylinder, but it's not drastically smaller. So it's about the inner cylinder radius.
Okay.
In the radial and axial direction, but in the azimuthal direction they are much longer. So it's a very long structure which moves around the whole system, and as it moves outwards, it's kind of a spiral structure.
Okay. So it's somehow almost periodical in azimuthal direction, going around the whole cylinder, but localized in axial and...
Not periodical in azimuthal, because in azimuthal direction it is having a radial component.
Okay, I see.
They have a start and an end of the structure.
Okay.
But we are doing more research on this, so it's
okay. Oh, really nice work. All right. Thank you very much. So then I think we can continue with the next talk from Siad Nantamushat. Hope I pronounced it right. And he will tell us something about patterns of convections. Okay, please go ahead.
Okay, so can you hear me?
Yes.
So good afternoon, everyone. I begin by presenting myself. So I'm Siad Nantamushat, a second year PhD student in Laboratory of Wave and Complex Media in Le Havre. And I'm working actually on the Taylor-Couette flow with the radial temperature gradient, directed by Innocent Mutabazi and supervised by Arnaud Priant. So today I'm going to talk about the pattern of convection in our facility, which is named TETACO. My presentation will be organized as follows. So I will do a small introduction, then I will show our experimental facility, and my result will be divided into pattern of visualization and temperature measurement and velocity measurement. So there have been a lot of studies conducted to investigate the heat transfer regime. There are three well-known transfer regime: conduction, transition, and convection regime. And the latest paper that took our attention is the paper of Lopez, Marquez, and Avila that concluded in the paper that the transition between the conduction and convection regime relies on a transition Rayleigh number, which depends on radius ratio and aspect ratio. So which leads me to our experimental facility. So this is a picture of our experimental facility of Taylor-Couette, which is named TETACO, and you have a drawing with all the specifications. The important part of my presentation is that with this facility, we can reach temperature difference between the inner and outer cylinder of 30 degrees Celsius, which correspond to a Grashof number to 1 million. And now with the experimental results, I will show you our experimental setup for visualization. So we have one continuous laser and a simple camera. So we did an experimental campaign with the temperature difference between the inner and outer cylinder from a range of 0.5 degrees Celsius to 27 degrees Celsius, which correspond to a Grashof number of 8,000 to 0.5 million. And the aim of this experimental setup is to have spatiotemporal diagram, gray level spatiotemporal diagram. So we take a radius in our laser sheet captured with the camera and in the gap, and then we post-process what happens during all the acquisition time. So the thing is, what is special about this facility is that we have with our smallest temperature gradient, 0.5 degrees Celsius, we are already in the convection regime based on a paper of Lopez, Marquez, and Avila. So this is what I'm going to show just after. Then we did another experimental setup for temperature and velocity measurements. Here, the thing is that we measured simultaneously the velocity by 2D PIV by doing 2D PIV, and temperature by using thermotropic liquid crystal seeding in our flow. Here you see an actual temperature gradient, which correspond to what just I said before, to the convective regime. And to determine the temperature, a calibration must be done to correspond a color into temperature. Now here we see two spatiotemporal diagram, gray level spatiotemporal diagram near the inner cylinder and near the outer cylinder for a low Grashof number. And as you can see, we have two main patterns. So near the inner cylinder, we have an ascending patterns that covers around 60% of the height of the facility. and the other descending patterns that covers all the height. So when we, as you can see also in the video here more clearly than spatiotemporal diagram. So when we increase the Grashof number to a higher Grashof number, we have the same behavior, except that the velocity of except that the velocity increase due to the increase of the temperature gradient. But we have also here in the upper in the top of our facility some interaction between the two patterns. Here you can see it more clearly in the video. You can see that we have interaction between the ascending and descending flow that create some disorder and some fluctuation in just the upper height. Now it's for the spatial-temporal diagram, and we decided after those spatial-temporal diagram to plot the evolution of the frequency and the wave number of our pattern. So for the ascending near the inner and the descending near the outer for in function of the Grashof, so Grashof number. So we see that we have a global evolution. It's not really a surprise since we already have seen it in the spatial temporal diagram. We can see that with the increase of the Grashof number, we have more speed and more frequency and more wave number. Now, for the temperature spatio-temporal diagram, so after the acquisition with the thermotropic liquid crystal, you can see a row red, green, blue camera acquisition in the bottom. We decided to plot now not gray level spatio-temporal diagram, but temperature spatio-temporal diagram. And you can see that for this measurement, we did it just for the third of the height of the from the bottom. So you can see the same pattern, same descendant pattern in this diagram. And also we can notice an actual temperature gradient even in the spatial temporal diagram here with the variation of 50 degrees approximately. That must be characterized. So as a conclusion here, PIV measurement are still in process. So we here I exhibit for you an actual velocity movie for the same high Grashof number, and we can see that the descending pattern has more velocity and more fluctuation than the ascending one. And so the aim after is to do the PIV and TLC measurement in all the height of the Titaco in order to determine the actual temperature gradient. And then we'll be able to investigate all the flow dynamics for this range of Grashof, which is 8,000, from 8,000 to 0.5 million. And after the aim is to include the rotation of the inner cylinder. Since our facility allows us to reach a high Taylor number up to 1 million, we'll see the effect of the thermal turbulence on the dynamic turbulence with the rotation of the inner cylinder. So that was my talk, and I thank you for your attention. I'm happy to answer your question.
All right, thank you very much for your presentation. I think we have time for some questions. Yeah, unmute yourself, speak up, feel free.
Perhaps I can ask a question. So I was wondering, how do you plan to measure the local temperature, let's say?
Local,
I mean, how do you use these? I mean, what is the basic mechanism behind it? How do you calibrate this, let's say?
In fact, we did already temperature calibration. In fact, for example, for this range of temperature, we have a temperature between 20 degrees Celsius and 40 degrees Celsius, and we put the inner cylinder and outer cylinder at the same temperature, and then we have homogeneous color, and then we capture. We captured each color correspond to 20 to 40, and with this calibration, we can know the temperature in function of the color. Yeah.
Okay. Yeah.
And it goes from red from the lower temperature to blue for the higher temperature.
Wow, that's very nice. That's very nice. And does this fluid have a special, let's say, can it adapt to the temperatures?
In fact, we are using only water, so PR7. But in fact, it's the seeding, it's the thermotrope liquid crystal that give us this information. Here, where is it? Here, we seeded our flow with the 0.077% of thermotrope liquid crystal. So it's those particles that adapts with temperature and change and give us a color in function of the temperature.
Ah, very nice, very nice, very nice. And this does not inhibit your PFE measurements at the same time.
No, in fact, it was surprising because we planned to add a laser shade in it, but just with the white light spot, it was sufficient for PFE measurement. Yeah, since the density of the thermotrope liquid crystal was high enough to capture all the small particles to reflect. The reflection was enough.
These particles are micrometers.
Yeah, exactly.
Okay. Nice. Thanks for sharing.
All right. Do you know, are there some numerical works available?
In fact, this is the question. I'm looking for numerical works that display patterns.
Yeah.
The only works I found are the scaling, turbulent scaling in Rayleigh-Bénard or Taylor-Couette or Pipe.
Yeah, I mean, that's the only thing what I was now thinking about, but nothing which is very close to that one. Okay.
Yeah.
Any further questions?
There's one in the chat.
The chat,
from Yin Wang. What is the typical temperature resolution of TLC? Can you?
Arno already answered, I guess.
The temperature resolution. How much can you get within, let's say, 0.1 degree or
temperature temperature resolution? I guess it's 1 degree.
1 degree.
For what I know, I guess.
And you go, what were your minimum maximum in temperature?
In fact, we have several thermotrope liquid crystal. Now we have a maximum of 40 degrees Celsius,
okay,
and a range of 20. But we also have for lower, for lower temperature gradient, we also have smaller scale, not smaller scale, smaller range. We have some that don't go from 20 to 40, but from 20 to 30.
Okay, you have different steps. Okay.
Yeah.
All right. Okay. Meanwhile, maybe the next speaker, Roger Ajax, you can already start sharing your screen. Or still someone has some more question to Ziad? No? Okay. I mean, if there are no further questions, I think we can continue. And now we will hear from Roger Ajax.
Yeah, sorry, I will share.
Okay.
I will share it now. Okay.
Okay. And now we will hear something about stable rotating waves in subcritical counter-rotating quad flow. Okay, please go ahead.
Okay, thank you very much. My name is Roger Ajax, and I've been working with Álvaro Meseguer, Yin Wang, and Fernando Melibowski in Barcelona, and also in collaboration with Ken Guadebuchi in Australia. And I'm going to talk about some stable rotating waves that we have found in subcritical counter-rotating region of Taylor-Couette flow. So I will begin with the motivation, computational domain, and numerical approach, and then I will try to summarize some of the explorations that we have been doing. So the main motivation of the research was to study the spiral turbulence in Taylor-Couette flow, which are these turbulent bands appearing in the counter-rotation region. So here, as example, just to show, I'm taking the well-known Andrek 1986 figure of the space parameter, just to show that spiral turbulence is located in this region here in the counter-rotating regime. And most of the expressions that we have been doing have been just centered in this small region. Actually, most of them for a constant Reynolds number of minus 1200 around this inner Reynolds number, and for a constant eta of 0.883. And more specifically, we wanted to capture SPT, the spiral turbulence in optimal domains, as we wanted to analyze to find some possible precursors of this SPT, understanding the precursors as some coherent structures that may contribute to sustain this SPT regime. So we wanted to follow some previous works in plane Couette, like, for example, the first one, Buckley and Tuckerman 2005, where they compute and study this turbulent laminar pattern by using this tilted but orthogonal domain. And here I'm showing other works that have been using this kind of domain. But what we are using now in this case, and we propose, is a generalization of this concept, redefining the computational domain. And actually, we wanted to follow and use the parallelogram non-orthogonal domain definition that was proposed by Deguchi and Almeida in 2013, where they computed some nonlinear interactions between spirals in Taylor Couette, so that the new directions of the computational domain were aligned, let's say, with the front wave equations, with the front wave of the spirals, so that now the new directions of the domain are defined with these two equations and with four wave numbers, N1, K1, N2, and K2. So starting with, of course, the Navier-Stokes equation, only for the perturbation in our case and the incompressibility condition, we discretize using a Petrov-Galerkin spectral solenoidal scheme method. And we are using a Fourier expansion in azimuthal and axial directions and Chebyshev in radial directions, so that the spectral expansion for the perturbation is this expression. And we also introduce propagation speeds here on the coefficients, so that for a rotating wave or a traveling wave, the norm of these matrices, the matrix coefficient, is constant, but all the modes are propagating with the propagation speeds. So introducing all this spectral expansion in the Navier-Stokes equation, of course, leads us to the nonlinear algebraic system of equations that we solve. And also, just for some visualization purposes, I want to define now the inner torque and the outer torque, and both of them are normalized with the torque of the base flow, the azimuthal circular Couette flow in our case. We have been used and we have worked with DNS time steppers, Newton-Coulomb solvers. Also, we use Poincaré Newton-Coulomb solvers and also Arnoldi linear stability analysis codes. So we wanted, and we want to do, we want to reproduce first the spiral turbulence in much smaller domains in a much more efficient way, so that we took as a reference some SPT explorations done by Meseguet et al. In 2009, and that were most of them done for these two Reynolds numbers. And which is important is the diagonal of the domain, so that for these explorations, the diagonal of the domain that actually is the same, well, the slope of this diagonal is the same than the spiral turbulence, and it is defined with this ratio N1K1 that was around 4.76. Now in these explorations, we take for simplicity this ratio equal to 1. So when we impose this ratio, now we are imposing that one of the directions of the computational domain is aligned with the spiral, so it's aligned with this diagonal, and we also impose N2 equal to 0. So actually, it means that we are also, the other direction is actually the horizontal direction. It's the azimuthal direction. So that the domain that now we are solving is this one, and of course, we can here reproduce the same spiral turbulence and for the big domain, but in a much more efficient way, because we use less, of course, much less modes and of course computational time. But we wanted to go further, so we wanted to analyze some of the existing solutions in these cases, so that we also imposed N1 to be 10, So actually we are now, our computational domain looks like that. So we are solving 1/10 of the total azimuthal domain, so that when replicating this domain 10 times in the azimuthal direction, it is perfectly fitting the complete annulus. So in this particular domain, we wanted to capture some stable coherent structures that coexist with the circular Couette flow, and we wanted to do some subharmonic analysis of these structures in order to see if we could find some relative periodic orbits that could be involved, or that could at least try if we could explain some of the sustainment of the SPT. And we wanted to find stable coherent structures coexisting with the stable circular Couette flow, because we know that SPT is a subcritical stable attractor when increasing, when going farther into the counter-rotation region. So a lot of experiments and numerical computations reported this behavior. So for the pure hydrodynamic Taylor Couette flow, Deguchi et al. In 2014 reported that in this region there are also some rotating waves that coexist with these solutions. Actually, here I'm plotting some continuations of these rotating waves from this work of 2014. And these are continuations of these rotating waves in inner Reynolds number. So when taking these first saddle nodes and we plot them here, it can be seen that, well, they coexist with the circular Couette flow and the stable spiral turbulence. So we wanted to begin analyzing these solutions and if they could be involved in this SPT sustainment. So that, as I've said, we have been focused in this outer Reynolds number minus 1200 now at the beginning, because we wanted to work in the easiest case now with the SPT that is supercritical for this inner Reynolds number, for this, sorry, outer Reynolds number. So we have done for some months a lot of explorations, and this the surface of this rotating wave for this new domain, it's quite complicated. But I will show here some examples of these continuations. Here I'm showing continuations in inner Reynolds number for this constant minus 1200 outer Reynolds number, and in black you can see continuations of these rotating waves, and they emerge from a Hopf bifurcation of from Taylor vortex. And when increasing a little bit the thickness of the domain, this is the K2 from 5.1 to 5, these two saddle nodes merge so that this scenario begins to complicate, and then we can find some disconnected branches in this case. And even further, when keeping increasing the size of the domain, in this case is for K2 4.5, the scenario changes a little bit so that these solutions do not bifurcate anymore from Taylor vortex, and they bifurcate from some other axis symmetric solutions, but they are some special properties. So the explorations of all these rotating waves in the new domain that we have done, we have learned that these branches are very sensitive to small changes of outer Reynolds number, and especially in thickness of the domain, that is this K2 actually. So just to give some examples here, I'm plotting the radial and azimuthal vorticity here in this case between it is the gap, so between the inner and the outer wall, for these points F, the upper branch, and A, the lower branch. And of course we have done, as we wanted to find some stable rotating waves, we have done a lot of linear stability analysis of these waves, and most of them are very unstable. But for this case, for K2 4.5 here, very close to the saddle node, we have found in a small region where these rotating waves are stable. And even more, we have found here a Hopf bifurcation, so that this leads to an stable modulated rotating wave that coexists with the stable circular Couette flow. So we have going further and we have analyzed in more detail this region. We have found some interesting results here that my colleague Baoying Wang will show you after the break in another talk. But just to summarize a little bit, the main goal that the works that the research that we are doing now, it's try to find some precursors of this SPT We have also learned, and we wanted to show that this generalization of the domain it's useful, because we have all the solutions that we have shown here were impossible. Most of them were very difficult to track in the orthogonal domain, as they were very, very unstable. So we have learned that by solving these solutions in another subspace, or solving the solutions in another domain, is changing a little, at least in our case, is changing a little bit the stability, and in our case, they gain a little bit of stability. So it is easier to work with this kind of solutions. And of course, this kind of domains are very, working with these domains is it's very easy when trying to do supermonic analysis, because they are easy to replicate and work with bigger domains. Also, we have found what we wanted to at least to begin with, so some stable modulated rotating wave coexisting with the circular Couette flow, that we should now try to do some supermonic analysis of them, and that my colleague Boying will try to show you also some interesting results. And there is some future work that we have already begin, and this is study the SPT directly in larger domains and trying to see which are the best domains to capture spiral turbulence. And this is something that is still in progress, and by now I cannot tell you anything more. So thank you very much for your attention, and if you have some questions.
All right, thank you very much, Roger, for your presentation. Yeah, as before, speak up. Maybe I can directly start with one, which goes basically what you said at the end for your future studies in that direction. Because I mean, it's a very nice, powerful tool, as you said, to make the calculation in these domains. But then, did you also, I mean, you already probably started with that, when you put this kind of solutions in the domains and try to follow them in the full domains, are they really all, I mean, I understand that the stability might change, but are they also all for sure existing there? Or then some of the solutions you might even not able to find them there?
Well, yes, exactly. If as the domain is not exactly the same, right. It depends on how much do you replicate this domain, so that if the corners are perfectly filling in the big domain, so the domain will exist there. Okay. Yeah? But if this domain, if you do not choose properly the domain, it is exactly, you can find some solutions that actually cannot be found in a real Taylor Couette or in a matching.
Sure. That's exactly. Because I mean you define a smaller domain, which then for sure it doesn't fit in the full one. Okay, so in that sense, you can somehow create some solutions that in the full one would not exist.
Exactly. So you have to be aware when you do these kind of simulations, because we always want to be physical, so that yes.
Okay, thanks. Yeah, other questions?
Mehdi, I think you're raising your hand.
Yeah. Mehdi, Leah? Yes. Unmute yourself. See?
Unmute yourself. Unmute yourself, Mehdi.
Mehdi?
There. No, Mehdi.
Yeah, Aaron. No.
There.
I don't know if you watch me.
Yes.
Yes, good. So my question concerned the existence of subharmonic instabilities in a system where there is no time periodic forcing, since you are interested in studying a case of Taylor Couette flow with steady counter-rotating cylinders, right?
What could you repeat, please?
So my question concerned the existence of subharmonic instabilities.
Well, we know that they will be, sure, they will be, when you replicate a lot of times this very small domain, a lot of instabilities will come up, so that for sure there will be subharmonic instabilities. But we wanted to show if some of the emerging solutions that could be there could explain a little bit the existence of this SPT. I don't know if I'm answering the question.
And in fact, such flow instabilities exist when the system undergoes a time periodic forcing, and we say that the system undergoes subharmonic instabilities when the frequency response is half of the frequency of the drive.
Mm-hmm.
So when you are studying steady counter-rotating Taylor vortex, Taylor flow, so how could such subharmonic instabilities occur?
Well, then when you take this small domain there, then you replicate it more times, then you allow that some perturbations with actually larger periods, yeah, enter to your domain, so that you will see these subharmonic instabilities, you know.
Okay,
Right.
thank you so much.
I would suggest, I mean, any kind of further discussion, you can do it now in the social room, which is, I put the link in the chat. It's basically the same as before. But before you go there, please stay here for 1 more minute, because you would get like another announcement by Rich. He will tell us something about a special upcoming issue for the honoring of Taylor's seminar paper. All right. Rich, are you there?
Yes, I am.
Okay.
Thank you.
Sander, do you share? Oh, perfect. All right.
Ah, there we are. Perfect. Hello, everyone. It's a pleasure to see so many people here. I'm delighted that we can all be here, and I want to thank Laurette and Sander and Sebastian for organizing this this 21st version of the International Couette-Taylor Workshop. But I also want to thank them for letting me tell you a little bit about this theme issue that we are preparing for the Philosophical Transactions of the Royal Society A. And as you all know, G.I. Taylor published his seminal paper back in 1923. So we're coming up to the 100th anniversary of that. And the impact of that paper has been tremendous. And not just Taylor-Couette flows, but general rotating flows and geophysical flows and astrophysical flows, fundamentals of fundamental concepts in fluid dynamics, which you've seen already this morning or this afternoon, drag and stability. And so we are preparing to put together a proposal for a theme issue of the Philosophical Transactions, and we've mocked it up there, and you can see that on your screen. I'm working with Rainer Hollerbach, Eric Serra, Randy Tagg, and I are working together to edit this version. We will be looking to publish this in 2023. So that would be 2 years from now on the actual centennial of Taylor's paper. But in order to do that, we have to get an idea of paper titles and authors very soon. We're looking at September 1st for that. Then we will put together a proposal to the editors of the Philosophical Transactions. And if they accept that, we will be looking for papers to be due in about a year, on September 1st, 2022, so that we can publish this in early 2023. The idea here is to put forth our best work from the International Couette-Taylor Workshop, the people who are attending this workshop. It'll be peer reviewed, but the idea is to draw together a wide range of contemporary research, all dedicated to this research that was started by Taylor back in 1923. We're looking for regular research papers and also review papers. So if you have any questions, you can ask any one of us. I saw Randy Tagg, I think, is here, and I'll be at the next available at the next break. I think Rainer Hollerbach might be. I haven't seen Eric Serra yet, but any of us will be happy to answer any questions, or you can send us an email. There's contact information at the bottom of this slide. And we'll also be contacting all of you by email after the workshop to see if you're interested in submitting a paper for this special issue. So thank you very much.
Okay, I'd like to say something, which is to say that although Sebastian and Sander and I have co-organized this meeting, it is actually Rich Leptov's idea. I mean, he kind of delegated us and put us together. He did matchmaking to put us together. So it's really, this meeting really comes from his idea, Rich Leptov's, to keep the meeting, Couette meeting alive.
All right, then I think now we will have a short break. So as before, the Wonder link is up in the chat, and then see you there, or later, otherwise in about 10-15 minutes here in the Zoom meeting. All right, see you there.
May I ask if there's any questions about going to the Wonder Me meeting? Does everyone understand? All you need to do is click, and then we're all figuring it out ourselves. None of us are experts. The idea is to socialize. Just try to go near the people you know or don't know. Right? Everybody understand? Just click on that link and then see what happens. Do your best. Okay. See you shortly over there. Mm-hmm.
Hi, Bao Ying. Do I pronounce that correctly?
Hi,
Bao
can
Ying?
you hear me?
Yes. Hi. Can you? I made you co-host. Can you share? Yes.
Now I'm sharing the screen. Okay, can you see the screen?
Yes. Perfect. Perfect. Yeah.
Okay.
Sound is also good.
Okay, so now let's begin. My name is Baoying Wang. Today I'm going to talk about the period doubling cascade of subcritical rotating waves in counter-rotating Taylor Couette flow. And as you can see from the outline that the first part about Hall bifurcation of rotating wave has already introduced by my colleague Roger Ayat. He has reported this figure, and here for this presentation, we are going to focus on this part. As you can see in figure 4, it's the index diagram. We are working in the counter-rotating region, and we are exploring in the subcritical region. We are solving the incompressible dimensionless Navier-Stokes equations of perturbation, and we're using a spectral discretization. This has also been introduced by Rouget. Also, we have developed Poincaré-Newton-Krylov solver, which makes us to be able to converge to the unstable periodic orbit. Here is the computational domain, and in figure 2, you can find the comparison of computational domain we are using with full domain. Here's a zoom-in figure around the southern node bifurcation point of the drifting rotating wave. After analyzing the stability, we found that at the beginning, near to the southern node bifurcation point, the drifting rotating wave is stable, and later on it becomes unstable because of a Hall bifurcation. This Hall bifurcation generates a stable relatively periodic orbit, as can be seen in the figure, that since it's stable, it can be obtained by slightly perturbing the drifting rotating wave, as you can see in figure 5. Starting from a slightly perturbed drifting rotating wave, the flow is attracted by this relatively periodic orbit. And for this presentation, we are using a viscous time unit. Instead of plotting one parameter changing with time, we can also plot the phase map projection, which is like this. Here I'm plotting the inner torque versus outer torque, and you can see a limit cycle here. This relative periodic orbit later on loses its stability and undergoes a period doubling cascade. So from now, I will call it P1. As this P1 is stable at first, and as increasing the Reynolds number, it becomes unstable. And when it becomes unstable because of the period doubling bifurcation, it generates another stable period orbit, which has nearly twice the period and half the frequency. For DNA estimation, we are able to observe up to P64, and here I'm plotting up to P16. And among all of them, P1, P2, and P4 are converged by the Poincaré-Newton-Krylov solver. As we know that there is a Figure-Mobs constant for the period doubling cascade, but however, it is time and memory consuming for computing all the bifurcation points for all these periodic orbits. However, we managed to compute the first ones and compute the delta J, which is the ratio related to Figure-Mobs constant. And they indicate that they are approaching to the Figure-Mobs constant. Now let's have a look at the whole cascade. Here you can see this is drifting rotating wave, and P1 generates a stable P2, later on P4, and finally it evolves into chaos. As we know that inside the chaotic attractor, there exists unstable periodic orbit. For example, this P1 becomes unstable but still exists. Here I'm not plotting it. If I plot the time signal of kinetic energy inside the chaotic attractor, we can observe that this is time signal, the kinetic energy. This is DNS signal. And we can see that it is bouncing between different periodic orbits. And we have managed to observe the unstable P1 and P2 for this Reynolds number and comparing it with DNS simulation. And here we can see the recursive visits to P1 and P2. If we increase a little bit the Reynolds number, what we can observe is like this. After 85 viscous time, it goes to Couette flow. So it is very small change in inner Reynolds number, but the behavior is very different because in figure 9, here we are only plotting the first 100 viscous time, but we have confirmed that it lasts for more than 500 viscous time. So what causes this different behavior? So in between these two Reynolds numbers is the critical Reynolds number. When we are trying to figure out what may be the explanation for this, we notice that just before it's renormalizing, it repeats a pattern like this almost 3 times. And actually, this is not the only Reynolds number we observe this. So it makes us to think that this could be another unstable periodic orbit. And finally, we converge it by the Poincare-Newton-Krylov solver. As you can see, it's like this. And if comparing with P1, the unstable P1 for the same Reynolds number, it has nearly 3 times the period of P1. So here we call it P3, although it is not the typical P3 in the period doubling cascade. Then we managed to converge and track this P3 solution. As you can see here, it is born at a certain node of cycles, as here after the P2 bifurcation point. And actually, we are using the Poincare-Newton-Krylov solver to track this branch because most of this P3 branch are unstable. And then we want to confirm whether or not is this P3 that causes the boundary crisis. Here in the left, I'm plotting a time signal starting from a converged P3. Here is the third iteration map, which means that here, if we consider here to be xi, then the xi plus 3 should have the same value as the xi because this starts from a converged P3 solution. As you can see, there are 3 minimal values, and in the iteration map, there are 3 red dots, means the converged P3 for the corresponding Reynolds number. And here we can see that the black dots here are the minimum point or the minimum value from DNS computation for the corresponding Reynolds number. So it is another way to show the chaotic attractor. Inside the chaotic attractor, when increasing the Reynolds number, we can observe that the attractor is growing in size, and then just before the critical value, it touches this P3 solution. And then after that, you can see a black dot here that it is going beyond this P3 solution, which means that this P3 is the explanation for the boundary crisis. Now let me plot the phase map projection just before and after the boundary crisis. So as we can see here, just before the critical value, the chaotic attractor is bounded by this P3. However, after that, it is not an attractor anymore. It becomes leaky and becomes a chaotic saddle. Here, I'm also plotting the lower branch of drifting rotating wave. We can see that it's far from this, this chaotic attractor. So it makes sense that this boundary crisis is caused by the collision of chaotic attractor with P3. Actually, this is not the first time that this kind of boundary crisis has been observed, because in Lucero's paper, they also reported a very similar phenomenon, which is also, the boundary crisis is also caused by the collision of sprint attractor with an unstable periodic orbit, which is not its origin, it's an unrelated one. And here we manage, when we are trying to track this P3 solution, we found that, to our surprise, that this P3 solution also exhibits another period doubling cascade, and it generates P6, P12. And what I should mention is that this part of the P3 is stable, and this P6, this P12 are stable here. So as we know here, there is another critical Reynolds number for the boundary crisis of this fringe attractor. And actually, if I plot just before and after this critical value, we can observe that for this one, before the critical value, it is bounded by this P3. However, after the crisis, it is not bounded by the P3 anymore. It's leaky to another solution, which is the P2 solution for this Reynolds number of the other cascade is not this cascade. So the renormalization of both the main cascade and the P3 cascade are caused by collapsing with the lower branch of P3. And actually, for this boundary crisis, there's another paper which reports a similar mechanism of crisis, which is published by Krylov and Eckford. But in this case, it's a little bit different. But this P3 could be understood as the origin of this chaotic attractor. And in their case, it's the fixed point lower branch. So let's make a summary that we have identified a Hopf bifurcation of drifting rotating wave that leads to a stable relative periodic orbit. And this periodic orbit later on undergoes a period doubling cascade until to permanent chaos. The boundary crisis of this permanent chaos is caused by the collision with the P3 lower branch. And as we know that this P3 also exhibits chaotic period doubling cascade, which also leads to another strange attractor that also collides with P3. So, and this P3 actually is born at a southern node of cycles. And actually, it is not the typical P3 in the period doubling cascade. Okay, that is all for today. Thank you for your attention.
Thanks, Baoying. Are there any questions, either in the chat or raise your hand and or speak up? So perhaps while other people are typing, I have maybe let's say a simple question. I didn't see it in your slides, but do these periods and these instabilities, do they depend a lot on the aspect ratio of the cell?
Actually, here we are fixing the aspect ratio to be the 0.883, and this is for all our explanation is fixing to this ratio.
But that's the radius ratio, right? I meant the axial extent.
You mean the thickness of the computational box?
Yeah, the height, let's say, of the cylinder. The aspect ratio.
Actually, yes, it may affect the stability. And actually, this is the only one that we observe with the upper branch near to the southern node bifurcation stable. So that's why here begins our story, because we found a stable part of the drifting rotating wave for this kind of domain. And we have tried different kinds of domains, different thickness, but they are more unstable than this one so far.
Okay, thanks. Are there any further questions for Baoying?
I wanted to ask this of Roger Ayat's last time too. This this computational domain you have, does that mean you have to add some terms, say to Laplacians? I mean, the differential operators, do they then acquire, say, the second order ones? Do they acquire first order terms and so on?
You mean to the governing equation?
It is non-orthogonal.
Excuse me, could you repeat your question?
Sure.
Sorry.
Computational domain, the axes are not perpendicular.
Oh, no.
So your equations have other terms. Am I right?
Yes. Actually, here is the one we are solving, the governing equation.
No, I mean, that's what everybody solves. That's not the extra terms. The extra terms, because of the axes not being orthogonal.
And actually, we are changing the axis in the, it can be seen from the spectral discretization. As you can see here, this U, we are doing it in the not horizontal domain, as you can see here. So we are doing it when we are doing this technique, when we are doing the numerical discretization.
You have special basis functions for these this domain.
Okay.
Yes. You have a special basis function. These.
Oh yes, special basis functions.
Okay, I see. Well, that looks nice. Thank you.
Okay, thank you.
Any further question? Perhaps a quick question. If that is not the case, thanks a lot, Baoying. And I would like to ask the next speaker, Vignesh Yeganathan, to share the screen.
Yeah, hi.
Yes.
Yes.
Good, I think.
Yeah. So can everyone hear me?
Yes, you have sound and vision.
Okay.
Yeah, go ahead.
Sorry. Hi, my name is Vignesh and I'm from University of Houston in Texas. My advisor is Dr. Astia. So my thesis is about controlling the secondary flows in Taylor-Couette flow. And so in the simulation section, I'm trying to add alternate free slip and no slip boundary patterns on the inner cylinder. As you can see, there are different patterns possible. So I explored different patterns and see their effect on the Taylor rolls. So in our case, we took the narrow gap and the aspect ratio of 2.33, and the outer cylinder is always rest, and the inner cylinders we went up to Reynolds number, we went up to 30,000. So this is a Reynolds number 30,000 with one pair of alternating patterns. As you can see, the plumes are rising from the no slip region, and the free slip region, not much is happening. So this is the inner cylinder. The left edge is the inner cylinder and the right edge is the outer cylinder. So this is the average velocity plot. And when you increase the number of patterns, so as you can see, the plumes which are rising, it's rising from two regions because there are like no slip conditions in two areas. So, and then when you increase the number of patterns, and it behaves as if there are no patterns at all. Like it's close to the regular Taylor-Couette flow, and we could see the plumes rising everywhere. And then we did some further analysis, and we did simulation for many patterns. And so this is for a regular Taylor-Couette flow. The rolls are there. And when we added the patterns, we could see the plumes rising from only one side, and the other side is nothing is happening here because it's a free slip. And this is a two pair of stripes and patterns, and we could see that the Taylor rolls are affected here. I mean, compared to the two images, we could see the Taylor rolls being distorted. And when we increase the number of patterns, as we saw previously, it's looking like a regular Taylor-Couette flow with the rolls intact. So we came to an idea that, okay, there is something happening at lower frequencies of alternating patterns. And then we further plotted the torque, and this left the axis, the right axis, sorry, the x-axis is actually the increasing frequency, as you can see, and the left axis, the left y-axis is actually the Nusselt number, non-dimensionalized by the regular Taylor-Couette flow. So as we can see, as a pattern frequency increases, our torque is also increasing, which is expected because at higher frequencies, the rolls are not seeing the pattern. The system is not seeing the pattern. But at lower frequencies of patterns, we could see there is a dip in the torque, and which we didn't expect initially. So, and then we studied, and then we did some fast Fourier transform, and we plotted the amplitude of the rolls. So we did the amplitude by taking the fast Fourier transform and using the first component. So we plotted the amplitude of the first component, and we find this dip coincides with the reduction in torque. So which kind of shows us that the rolls are becoming weaker because of these patterns. And so this kind of phenomenon is observed only at higher Reynolds number. As you can see in this plot, for different Reynolds number, the torques are increasing at lower Reynolds number, 722 and 2280. At these Reynolds number, it's increasing, but after Reynolds number 10,000, it starts behaving the behaving the way which I showed in the previous slide. So we found this very interesting, and later we try to see if there is any boundary effect on the flow, and is that why it's happening, or is it because of the rolls itself? So we plotted the effective slip length and the effective slip velocity, and I mean there is not any dip or any anomaly, like any difference from the pattern like we saw in the torque plot. It's like they're constantly, like they're monotonic, they're like they're decreasing, and there is no like a huge dip. So which kind of shows that the distortion and the roll is caused, the torque reduction, the torque is caused by the distortion of the roll and not by the boundary which we are putting in. Not the boundary is not the direct cause of what's happening in our system. So as we see, the slip velocity is also decreasing when the pattern frequency is increasing. And so then we went to some interesting patterns because spiral patterns, when they start rotating, the inhomogeneity kind of moves, starts drifting. Say if the cylinder is rotating in an anti-clockwise direction, so these pair of inhomogeneity in the left edge, they start going downwards relative to the cylinder. The spiral pattern will slowly start drifting. So which we've kind of found it interesting. And then we defined a few parameters such as wavelength in Z direction, wavelength in X direction, and wavelength in alpha direction. Alpha is the angle. So we call the motion at which the stripe drifts downwards and leftwards as like VS Z and VSX. So and then when you see, like when you, for different alphas, for different angles, the stripe will move at this is plotted geometrically. The stripe would move at faster, and then it will slow down. The negative sign indicates the direction. And yeah, so when we did the simulations for Reynolds number 10,000, as you can see, the Taylor roll starts here, and slowly it starts moving downwards. If you see the plumes where it's rising, it's kind of moving, drifting downwards. So actually what happens is, because of our inhomogeneity, since the spirals are like moving downwards, rolls are also following the pattern, the way they move downwards. And and then we try to plot the induced velocity, the velocity in Z direction, and we saw that, and then we plotted along the radius, and then we saw that some axial velocity is induced in the system, and at higher angles not much, but at lower angles there is definitely the rolls are pushed downwards because of the inhomogeneity. And then when we plotted the inclined stripes, and for Reynolds number 10,000, and for a particular angle and number of stripes, so what we could see is, when we plotted the average, we couldn't see any rolls. And this is kind of expected, because since the roll is moving downwards at time, the signature of roll doesn't appear clearly in the average velocity. And when we did the space-time diagram, we could see the rolls like clearly move. As I showed in the video previously, I showed only few time step, but this is for 40 time step. You can clearly see the rolls of moved, drifted downwards. And these, the red lines and yellow lines are phase angles from the Fourier component obtained during the fast Fourier transform. And again, after at Reynolds number 10,000, we plotted the roll velocities. I call roll velocity when, it's not the velocity of the rolls, it's the roll drifting downwards. That is what I call as roll velocity. So here, when the frequency is increasing, the pattern frequency is increasing, we could see the roll velocities, the velocity at which the roll move downwards increases, and then after some point it starts decreasing. And this kind of trend is observed at other 30,000 Reynolds number as well. So as you can, and this left plot is just the velocity of the roll, and then the right plot is the velocity of the roll as a percentage of the stripe motion. The pattern itself is moving downwards, and the roll is tracing it. as you can see, the highest possible value at which the rolls moves only 3% of the stripe velocity. And that is more predominant at lower angles. Since we saw in the induced velocity plot previously, like the lower angles are, at lower angles, the induced velocity is more. So we found that same phenomenon in Reynolds number 30,000. Like these lower angled patterns are very efficient in moving the roll downwards. That is the takeaway from this slide. And it is good at 36 degrees. I mean, it's great at 20 degrees, and then and it slowly, like when you increase further, it slows down. The roll slows down. Maybe the roll is not able to keep up with this stripe motion. I guess like it needs to be of certain magnitude or less for the stripes to move. And the summary of this study is it's a purely simulation study, and we saw that the Taylor rolls are distorted because of this pattern, the axial inhomogeneity, and because of the spiral pattern, we could see the induced velocity like move the Taylor roll, and then the other patterns. I mean, since we have curvature, there are so many different patterns possible, but these are the few basic patterns which we could come up with, and add some luck with the results. And these patterns, they don't have much effect on the Taylor rolls. And so this work can be seen in the archive, and it's being accepted for publication in JF, the Journal of Fluid Mechanics. If you have any more questions, you can contact one of the authors here. Our email ID is listed here. And any other questions?
Thanks for your talk. Are there any questions? Either raise your hand, type it, or speak up. In the meanwhile, in your previous slide, I have a question on, so you wrote down the Taylor rolls are not affected, but what about for example, the RMS velocity in the boundary layers and things like that? Are those impacted a lot? Because I can imagine that it has to switch between, let's say, no slip and no shear every time, let's say.
Okay, you're asking if the boundary is affected?
Yeah, so let's say the velocity fluctuations in the boundary, for example.
Yes, sir. I mean, the boundaries were affected, but we were looking at the larger scales. We were interested in the Taylor rolls. And certainly there were, like, if you visit the paper, you can see, like we have showed images near the boundary. We could clearly see the pattern of the signature of the pattern on the rolls on the boundary layer. But it's not an interesting result compared to the rolls itself, like how the rolls behave. Yeah, we could see the signature of the pattern, and there are like strong gradients between the patterns from the no slip to free slip.
All right.
Yeah.
Thanks. There's also a question in chat from Sebastian Merbold, and he asked, "What's the motivation of simulating these slip regions?"
Sorry.
What's the motivation of simulating these slip and no slip regions? Let's say.
So you're asking, how did I do that in my simulation?
No, the motivation.
Motivation. Okay, the motivation we derived it from Rayleigh-Benard flow. I mean, I didn't show it here because it was a 10-minute talk. Okay, in Rayleigh-Benard, we have seen people using heart region and I mean the adiabatic and conducting areas to play with the heat transfer. So we did the exact same thing in Taylor Couette flow by using free slip and no slip condition to play with the angular velocity transfer. So we thought like maybe we might have some luck doing that. And there were previous studies which did roughness, and there were few studies which did slip lengths as well. So we thought let's just go to higher Reynolds number and use DNS and see how it goes from there. So that's when that's the motivation behind our problem.
All right, there's another question in the chat from Yin Wang, and he asks, what are the boundary conditions in the axial direction? Is it periodic or not?
Yeah, it's periodic. We just simulated one pair of rolls and two pairs of rolls, and I can show you some of the, for example, if everyone can see the slide. So this is a periodic boundary condition, and we could see here like this is 2.33 Taylor
Yeah,
roll. This is 3 Taylor roll. The number of rolls and stuff. When you simulate the two pairs of rolls, we could see the similar effect. And we did the domain dependent study as well. It's a periodic boundary condition, yes, sir.
All right, and there is a final short question by Suhail. What about the secondary vortices which form at the point of the meeting of the slip and no slip areas, as reported in channel flows at low Reynolds? Do they appear in such higher Reynolds?
The secondary vortices are actually we only did the averages, so I didn't see the instantaneous effects. In the average plots, we didn't observe any secondary vortices. I mean, there were plumes rising, but we haven't focused our study on that. We were focusing solely on the Taylor rolls and its effect, patterns effects on the Taylor rolls.
All right. Thanks for your time. Thanks again.
Okay.
Now the next talk will be given by Michael. Good morning, Michael.
Morning. Yeah, I'm here.
I thought you just woke up, indeed. I just didn't see you before, but I can imagine what time it is now in California.
It's not too early, but we had a big holiday yesterday, so we're all getting up.
Okay. Good morning. You should be able to share your screen.
Yeah. Here it goes. Is that visible?
Perfect. Yes. Maybe you can make it larger, like how you call it?
Right. 1 moment.
Presentation mode. Yes, perfect. Yes, go ahead.
All right. Well, good morning or good afternoon. My name is Michael Buren. I want to report on just some very preliminary experiments from the past year or so done in my lab at Cal State San Marcos, which is in near San Diego in California. This is work pretty much did by myself, but I'm expecting a couple undergraduates to join me a little later on in the year. So I'm tentatively calling these longitudinal instabilities. I'll explain the tentative nature of this momentarily. Observed with unsteady and namely a start-stop motion of the outer cylinder. And this was inspired by a figure that was really mentioned in passing in Cole's classic paper from the mid-1960s. In figure 22D, you see a short little description saying instability following start-stop motion of the outer cylinder. And you can kind of see these modes that extend along the axis away from the end caps through the bulk of the central region of Z. So the smaller gap size, about 1.5 centimeters, aspect ratio is about 14. Again, the axial alignment of the dominant mode here. And these modes appear distinct from other studies and instabilities of unsteady Taylor-Couette motion. And so I set a goal to recreate, identify, and then characterize with visualization and then velocimetry. So just a bit of brief, not very comprehensive, but just to survey the landscape of unsteady Taylor-Couette flow, featuring some sort of time-dependent motion of either the inner and or outer cylinder. You have monodirectional inner cylinder acceleration, so impulsive starts. The resulting Reynolds number based on the inner cylinder speed here is not unique, but it's not due to hysteresis. It's rather due to the rate of change of the rotational motion, again, of the inner cylinder in this case. There's also what's been called or termed modulational Taylor-Couette flow. So this is where the inner cylinder, either with a zero mean or with a finite mean, with the outer cylinder held fixed at zero velocity. There's also with a finite inner cylinder and a modulational outer cylinder with the inner cylinder held constant, usually at a finite velocity or rotation rate. And I'm excluding here what's also added to this term MTC or modulation Taylor-Couette, axial oscillations of the cylinders. And then we've had some interesting recent work that you're going to hear more about tomorrow, I believe, where there's significant monodirectional outer cylinder deceleration in this case, or what's termed sometimes or mentioned as an abrupt stoppage. So recent interesting work by Sinjin Pujant from earlier this year. And from what I can tell at this point, most of these feature varying degrees of Taylor-Gortler vortices, and the impulsive start-stop motion that Coles briefly pictured seems to still be unexplored. So a bit about my apparatus. It has an outer cylinder radius of about 20, I don't say it here, 20.9 centimeters, allowing for a narrow gap of about 6.5 millimeters, aspect ratio of 92. Those are the experiments I'll mention here. But I have interchangeable inner cylinders, so I can feature a much wider gap with a radius ratio of 0.55, aspect ratio of 6, and then something in the middle. So small, medium, large cylinders, inner cylinders. It has two independent DC motors. This allows for speeds up to about 1,000 RPM, max Reynolds numbers near 1 million. Clear acrylic top for vertical diagnostic access, namely LDV. And then for the smallest inner cylinder, the end caps can be coupled to either the inner or the outer cylinder, or split with 50-50, where half goes with the inner and half goes with the outer. So I'll show you a brief movie of the initial effort to recreate this. Then it plays again at a reduced speed. Those are the waves of interest currently. So a few additional comments. Pause it here. So this observed, again, what I'm temporarily calling longitudinal instability is distinct from the end cap turbulence, which is proceeding from both sides and meeting in the middle. I'll find that point of the movie here. So you can see that well developed along the top and bottom end cap. And then when the instability is seen, whoops, sorry. Eventually it all merges, but there you can see how the instability starts distinct from the end cap turbulence, though it may have had some sort of triggering from it. Remains to be seen. So this is only seen, I tried this temp. You can see temporarily the very high-tech forcing mechanism by hand, but I'll explain that in a moment. This is only seen with my narrow gap arrangement, not with the medium or larger gaps. I have simple clearoscope imaging here. The apparent is during a period of outer cylinder deceleration, and I think that's significant. But the exact annular velocity profile, which of course is very significant, has yet to be determined. It's increasingly corrugated, larger fluctuation of the wavelength, standard deviation and all, but the eventual merging of different turbulent regions. But the final state, if we go right to the end, not too dissimilar from the wavy or Taylor wavy vortices. Okay, onwards. So the typical outer cylinder acceleration profile, again, by hand, is just shown on the in this little diagram here. Again, right after a second or two is where we see the onset of the instability. This is acceleration plotted over time. And the key question here is, how does this acceleration profile translate to a radial velocity profile in the narrow gap? Just kind of an interesting note for students. If everything stayed laminar, it would be a nice little, and if the oscillation was sinusoidal, it'd be a nice relation to Stokes' second classic problem, which is shown as a little GIF here. And clearly, by hand is not ideal for systematic study. So ideally, I would have motors that have infinite torque and are very fast to respond, neither of which my current motors do. But I wanted to at least have a start at looking at this more systematically. So we built, based and inspired by some of the viscometry experiments by Couette and Maluk of the late 1890s, we built kind of a pulley system where different weights could be dropped accelerating through a torque of the outer cylinder. Just a few pictures here. So the idea is to drop different masses, increasing mass at different amounts of time, letting it fall different amounts, thus accelerating the outer cylinder in a more steady way. And some initial experiments from this first attempt. We notice that the wavelength of this mode increases with increasing maximum acceleration. So here's an example of a higher acceleration, a lower, higher in red. Here's the average wavelength of the instability. There's a acceleration below which we don't observe it. And again, it's not observed with the wider gaps. And then there's an acceleration that's high enough to where the end cap turbulence kind of meets in the middle before you're able to see the instability in the middle. So that's something of an upper boundary. It might still be there, but it's not viewable. So maximum acceleration is just a temporary parameter. It's also a degenerate one because heavier weights, because it's driving a torque, will create larger accelerations. But you could also get larger accelerations with the mass falling for more time, which allows the velocity to penetrate with more time into the interior. So, and this of course affects the radial velocity profile. So again, it's a degenerate temporary parameter, but for what it's worth, a couple initial results. The next steps, of course, is not to do things by hand or even by falling weights, but to have at least a refined mechanical or a motorized system to systematically, repeatedly explore a range of outer cylinder acceleration profiles, focusing on the start-stop, but again, there's a lot of range here that could be explored. And then to use LDV, as was done in some previous experiments we'll talk about in a moment, to characterize the velocity profiles over annular radius and time, usually as an ensemble average, I would imagine, given the quick nature of the motion. And then ultimately to link to boundary layer theory. What is the exact role of shear? Are these just TS waves on a convex surface? Quite possibly. That remains to be seen, but quite possibly. And I'll point out that simulations of this are welcome if you fancy having a shot at recreating this, because I've yet to, at least in the Taylor-Couette context, yet to see something like this. I mentioned, next slide here. Yeah, so some previous velocimetry across various gap widths indicate that the narrow gap arrangement that I'm featuring here is unique in that there's an inflection. The turbulent profile in the upper left here has this inflection going throughout a meeting. The meeting of two boundary layers is almost apparent. By contrast, the medium gap has the concentration near the inner cylinder, a more gradual profile. This is laminar and turbulent experimental measurements in B square and Dynan respectively. And then you can see the effect, even though it's not pertinent here, the effect of the end caps is great when you have a wide gap. When the end caps are coupled to the outer cylinder, all the shearing happens at the inner surface. And when the end caps are coupled to the outer inner cylinder, all the connection and shearing happens at the outer surface. Okay. And this is also mentioning going back to the narrow gap profile, which is pertinent here, also seen in simulations. So in conclusion, these so-called longitudinal instabilities are observed in Taylor-Couette flow with a start-stop outer cylinder motion, inner cylinder is held stationary, similar to that pictured by Coles. Some very initial findings from a mechanical pulley system shows that the wavelength depends on forcing, increasing with maximum acceleration. Previous experiments with LDV with this system indicate that boundary layer shear plays a key role with a narrow gap. And so some post-COVID systematic experiments as the labs open up here in the coming months are planned with undergraduates at my institution. So thank you for your attention.
Thanks for your talk, Michael. There is time for one small question, either in the chat or raise your hand.
I had a quick question about the wavelength. And how does that wavelength compare to the gap thickness? I couldn't read that on the slide.
Let me go back to it. It's comparable. It's a little bit, it's a range. So it starts at a little over 1 centimeter, maybe 1.25, and that's about twice the gap width, the smallest one I see. And then the largest one I see is more like 4 times the gap width.
All right, Mehdi, if you have a quick question, please.
So I have a question concerning the mechanism of instability, since as one can see, it's this longitudinal instability could clearly distinguish it from the classical Taylor-Couette flow. So how could we, for a better understanding of the appearance of this kind of instability, so what's the mechanism responsible of their appearance?
Well, that's the question I hope to address, actually. Really, without knowing the velocity profile and the degree of shear at various points within the gap, it's hard to identify. It's reminiscent to me of a classical boundary layer instability like TS waves, but again, I'm reticent to put a name on it. I certainly wouldn't call it new at this point. But once I have velocimetry for various acceleration profiles, that would be able to be addressed more carefully, more thoroughly.
Thank you so much.
Thanks, Michael, for your talk. As we will now go to the next talk by Rodolfo Stiamonico. Rodolfo, are you able to share your screen? Perfect.
Cool.
So Rodolfo did his PhD here in Twente under the lead of Detlef and Roberto Vrzico. I don't know if Roberto is here as well. Then he went to Harvard, and now he's an assistant professor in Houston. And he will talk about his, well, the last decade of him doing simulations, basically. Go ahead, Rodolfo.
Hi, well, thanks for inviting me, and thanks for putting up this virtual event. It's actually really cool. I don't think I would have made it if it had to travel again. And I took inspiration from my PhD advisor, Roberto Vrzico. He said, like, if you give an invited talk, you should try to give a wide overview. So I said, well, this is probably the thing I can give the widest overview of, because it was my PhD topic. I actually started 10 years ago in Twente, around May 2011. So basically, the first slide is the usual thing, geometric parameters, Taylor-Couette. And I will try to focus on one of the things we normally use in Taylor-Couette.
Rodolfo, could you turn on your video as well, your webcam, let's say? For those people who cannot, they somehow need visual cues to hear better.
Oh, I'm sorry. Yes. Does this work? Can you see me?
Yeah.
Yeah. Cool. So basically, Taylor-Couette, the flow between two concentric cylinders. You have two geometric parameters: radius ratio, eta, aspect ratio, and then we have two driving parameters, which you can basically pick whatever you want to write them as. So you can write them as inner and outer Reynolds number. You can also write them as a shear and a rotation parameter, and there's many ways of writing a rotation parameter. You can also follow the analogy with Rayleigh-Bernard and write it as a Taylor number that's roughly a Reynolds shear squared. So when I began my PhD, I remember arriving as a person who's like coming from engineering, and they gave me these two papers, which was basically the classical Anderegg Lewis-Winnie phase diagram for Taylor-Couette, and some results from the recent experimental work in Twente, which basically showed the torque scaling of Taylor-Couette at very, very high Reynolds numbers. And it also showed how the torque depended on the way you spin the cylinders. So if you spin more the inner than the outer one, or you spin more the outer than the inner, you get different torques for the same driving, and there is a maximum. So this was basically like my starting point. And also at that time, I think I was really focused on the analogy between Taylor-Couette and Rayleigh-Bernard, which Mark Avila talked quite a bit on this morning. And the paper by Bruno, Detlef, and Siegfried on how they expected the torque to scale in turbulent Taylor-Couette. So my first task, and this is, I guess, where I started thinking about Taylor-Couette. I mean, I started thinking, if at all, started a PhD. We had this parameter space, which had a few points on it, both experiments and simulations, but there was a big gap between what you have here, the small gray rectangle that was the Anderegg paper, and the new experiments, both in Maryland and in Twente, that are represented by some blue diamonds and some red dots here and there. And the crosses which appear to bridge it are actually Wendt's 1937 experiments. So you can imagine the resolution and the PIV was not really an option back then. So the questions I started thinking about a long time ago was, how does a torque behave? And how does the flow look like? And how does a change in the flow look like? How does the flow change as you go from the gray rectangle to all the way to red squares? And the last one, which I started thinking about more recently, is can we control how the flow looks like? So what kind of things can we control from the flow, and what kind of things do we have to like live with? So the first question actually was probably the first half of my PhD, or the first 2/3. And it was trying to capture what was basically the question of the time, which was how does this flow transition to the ultimate regime, or basically the idea of when does this flow reach some asymptotic scaling laws, that the torque as a function of driving reaches a certain scaling law that is basically higher than 1/3, which means that in the Rayleigh-Benard analogy, it means that this flow is fully turbulent. And we did some simulations, and this is the same time the group at Marburg was also doing some DNS. And we were able, I think this is a really beautiful picture, because we have two sets of different simulations and two sets of different experiments, and they all overlap with each other to 1–2%. And I don't think you can get this very often. And we all found that there was a transition between what you call the classical turbulent regime and the ultimate turbulent regime, where the boundary layers are also turbulent and not just the main flow. And this happened at around Taylor 3 × 10⁸. That's approximately a Reynolds number of 10,000 for reference. We also looked at how this curvature, basically what happens when you make the cylinders, the radius ratio between the inner and the outer cylinder different. When does this transition take place? We found that, as long as you had a small degree of curvature, eta 714 or eta 909, which were the two we used to work more at the time, is basically if the inner cylinder is 1, the outer cylinder is 1.4 or 1.1, then the transition happened more or less the same Taylor number or Reynolds number. You start increasing the curvature, eta 0.5, so basically your inner cylinder is 1 and your outer cylinder is 2, then this transition seemed to not take place at the time. We didn't, at least I didn't give much importance to that and at the time, because the other thing we were much more interested in looking at is what happens with the differential rotation of the cylinders. So going back here, we have basically the lab frame, where you have the inner cylinder rotating and the outer cylinder rotating. And we could recast this as a rotating frame that rotates with the outer cylinder. And then your two control parameters, which come as boundary conditions, and that's never nice, actually they appear in the equations, and you get this Rossby number, inverse Rossby number, which basically tells you how strong the rotation is. And you reduce this differential rotation of the cylinders to a Coriolis force. And if you think about it, this reference frame was very reminiscent of Rayleigh-Benard in my head at the time, because now you have only the inner cylinder rotating, and that's the Rayleigh-Benard problem. You have an instability because you have a centrifugal instability. We did this and we found that the transition again to turbulent regime was not that dependent on the value of the differential rotation. So most of the flows, regardless of where you decided to, or how you decide to rotate the cylinders, were transitioning at, again, Taylor number 10⁸, Reynolds number 10,000, 20,000, more or less. What was puzzling, and was very puzzling, was this fact that the curves appeared to be ordered again. You have a maximum Nusselt number, a maximum torque for a certain value of the rotation. And once you look at across all experiments and simulations, you found that, well, if you express things in this Rossby number, things look very, very far from collapse, right? You have a lot of different geometries here going all the way from eta 0.5 from the Cottbus group down to eta 0.91 from our simulations. And you really see that there's no real nice way of collapsing things. The maximum transport basically depends very strongly on the curvature. So this bothered me for a while. And what we started looking at, and other people started looking at, predominantly the group in Marburg, was does the flow look like, and what can we say about the flow? And the thing that we found that struck me and struck, I think, many people in the turbulence community is the fact that you have basically a persistent Taylor role. So you have these turbulent structures that persist even if your boundary conditions are periodic, right? They remain there. So this is what we show, a cut through the cylinder. And if we were to average this, you get a very nice structure or signature. Reynolds 10 to the 5, you have a very strong signature there. You don't know why, but it is there. And what you also know is that if you start looking at where this structure appears in parameter space, this structure appears very, very, very close to the optimum transport. So it appears very, very close to regions in parameter space where we had this peak in the Nusselt versus rotation curve. However, at the time I was thinking about this again in the analogy of Rayleigh-Bénard, and my idea was that, curvature and mean rotation prevent the existence of rolls or give you rolls, because inherently I thought that these rolls were always tied to the idea of centrifugal instability. And that's true at low Reynolds number, but something I come very, very slowly to realize is that this is not true at high Reynolds number. And we will go into this a bit later. The other thing is that experiments were also able to see these rolls at very high Reynolds number. 10 to the 6, you have these fixed structures. Because a lot of people, and this is a very legitimate concern, I feel, asked us is, are these rolls real? Because in experiments, of course, you have end caps that kind of situates the rolls. In experiments, if you use very small computational boxes, if you use a periodicity lamps that are too small, you end up creating artifacts. So a legitimate concern was what these rolls, were they artifacts or were they actually appearing in our simulations? So something we did is we ran an extremely large simulation, which was of turbulent Taylor Couette, Reynolds 15,000 and Reynolds tau 240. We ran it for a very, very long time, 29 viscous time units. And this was an extremely large computational box. So 21 pi in one direction, 9 pi in the other direction. And we found that, even for this case, we had 7 pairs of rolls. However, the problem with this is you can always make your box twice as large, right? And saying that you can always make it twice as large gives you very little handle on things, because someone can always question you or object that you can always be twice as large, right? We want to simulate the infinite case. You can always do twice as large, and you will never stop this process. I mean, especially in channel flow, there's people who run maybe 200 pi or 400 pi computational resources. There's always the option to put one more data point. The other interesting thing we found is we are able to replicate this idea from experiments that you could have multiple solutions. So here we're showing the azimuthal velocity, which is averaged for different initial conditions, extremely high Reynolds number, 34,000. And if you do that, you actually, depending on the initial conditions, you can actually get a 2-roll state or a 3-roll state. And these persist again for 50, 60 viscous time units, which is what we ran. Extremely stable solutions. And I felt that this was one of the more interesting results back at the time, and I still think so, because it tells us that, there is a certain hysteresis to even in the strongly turbulent regime, and we can look at this so it can begin to teach us things about, what can we expect as the Reynolds number becomes arbitrarily high. However, this did not solve our problem. Going back to the graph, torque against rotation ratio, still almost impossible to collapse. And this is when this other paper by the Marburg group came along, which actually showed collapse between all the radius ratios, all the way from 0.5 to 1, and for a single rotation ratio or single rotation parameter. And what they were doing is they were not using the rotating frame where you rotate with the outer cylinder, but they were instead using a rotating frame where you have what you call a convective frame. The idea is that instead of rotating with the outer cylinder, which I saw as a Rayleigh-Bénard analog, They use a plane Couette analog where both cylinders move in equal but opposite directions. And the thing about this convective reference frame is that you can actually show that this doesn't become singular as you take the curvature to 0. If you look at the left parameter, you have this 1 minus eta dividing, which shows that as eta becomes 1, so you reduce curvature, you actually become singular. Here on the right, there is actually a finite limit to this. You can actually take the limit and you end up with this rotation parameter which exists. So then I started looking much more at this convective frame. I started looking at Taylor-Couette much more from the point of view of plane Couette flow. And this is like saying, and now instead of talking about co and counter rotation, we can talk about cyclonic and anticyclonic flows, where this solid body rotation can be either aligned in the direction of vorticity, which is cyclonic, or it can be opposite to the direction of vorticity, which means it's anticyclonic. The particular thing about this is that this parameter is actually dependent on eta for inner cylinder rotation. This is telling you that as you increase your inner cylinder, your curvature, you're actually adding more and more solid body rotation. And this gave me a lot to think about. And this whole line of thought eventually, oh, sorry, there's one more slide of equations. And this, I think, talks back to Mark Avila's point, you know, everything in green here, this is equations for Taylor-Couette in this rotating frame. Everything in green here becomes plane Couette when you take the curvature to 0. Everything in blue is actually your curvature correction in a way. So you can see how these terms are actually going to be very small when you have a very small curvature, but they're going to be very, very increasingly large as you increase it, as you increase the curvature. And using this inspiration, we try to take some page out of shear flows and use basically Walef's self-sustained process as a way of understanding the Taylor rolls. So to summarize, what we did is we took the velocity field and we filtered out, we took azimuthal average. So we take U, which is still time dependent. We just take out all azimuthal information. We average in the azimuthal direction, and we use that to define streaks and rolls. And if we do that, we can actually show that as you increase the box size, if you have inner cylinder rotation, the roll streak amplitude is almost constant, which means that this thing is actually stable as you increase the box size. If you have outer cylinder rotation and you have nothing, these axisymmetric modes actually go down. The energy in these axisymmetric modes goes down as a function of box size, and it goes down as a function of box size to the -1, which is what you would expect from some sort of aliasing modes. And with this, we were able to show that the rolls are actually physical in our simulations, but also that, you know, it doesn't matter how big or how small your box size is, you will always have some sort of effect. And it's very, very hard to get box size independent results. This is another thing we did, is we started looking now from this plane Couette reference frame, and we look at the Coriolis force in this case as a double coupling term. So you are the radial velocity couples on the azimuthal component and the azimuthal velocity couples on the radial component. You think of the Nusselt number as a correlation between UR and U phi. Inside the boundary layer, wall normal velocity fluctuations are much smaller than your azimuthal fluctuations. Rotation will increase the small radial fluctuations without significantly affecting the azimuthal fluctuations, and this way you can increase transport. And there's a parallel here between the 2D axisymmetric plane Couette or Taylor-Couette flow that Mark was talking about this morning. Because if you think about it, you know, here we plot the mutual information, which is a way of plotting a correlation. Inside the boundary layer, the information between U, the azimuthal, and the radial velocity, they're more and more correlated as you increase the rotation parameter. At the mid gap, though, that correlation does not survive because now you have an opposed thing. One case you have a positive sign, one case you have a negative sign. One is breaking the correlation, that the other one is inducing. Very, very close to the wall, UR is 0 essentially, so you're only inducing correlation. far away from the wall, both terms become of the same size and you're breaking correlation. And we can use this to understand optimal transport in the sense that as long as your rotation is very, very small, you induce a bit of correlation. But when your rotation becomes very, very large, this double coupling destroys the correlation. And you can see how basically the streaks are strongest when there is no rotation, but the roll is strongest when there is some weak co-rotation, right? And this is what's telling us, giving us a way to understand this optimal transport in the very turbulent regime once you lose this plane Couette analogy. Sorry, when you lose the Rayleigh-Bénard analogy of the 2D flow. Some more things we found, well, basically the rolls only exist when the coupling is small. You know, when you have R omega equals 0.1, you get very strong rolls. When you have R omega 0.5, you completely wipe out the rolls. We are able to make the rolls survive all the way down to zero curvature. We look at the fundamental Fourier mode energy. It goes down a bit, but it doesn't go to zero. It's still extremely high for no curvature. And we also started looking at what happens when you take away the no-slip wall. So we did some simulations of wall F flow, basically stress-free walls. You force the flow using a body force because now you can't force through the walls, and you add some rotation. You have, again, two dimensionless parameters, one Reynolds number, one rotation parameter. You now look at the average streamwise velocity. In this case, you have a fixed shear because you have a fixed body force. So an optimum means the smallest velocity required to transport the fixed shear. You see here we have a lot of curves, but essentially there is an optimum, and it happens around 0.63, 0.79. You can look at that, and you can also look at the flow. You see how we also get rolls for this case where there is no wall, and the rolls are strongest around the points where we have the optimal transport. You can actually measure this, quantify this. You don't have to believe me. Mean streamwise kinetic energy reaches a plateau around 0.5, and the average roll circulation is the highest at 0.5. So we are able to show that, you know, you don't really need boundary layers. This is a fully bulk effect causing the rolls to happen. So then for the final few slides, the question becomes, you know, how do we affect the rolls? Which for me have been the most interesting thing I think I've been looking at for the last years. Well, we did some studies some long time ago. We tried to modify them by doing riblets. Well, actually, you don't modify them at all. This is the Nusselt number. The correlation remains the same whether you put riblets or not. You stop the cylinders. You stop the forcing. The rolls don't stop for a while, which tells us they're extremely resilient to any sort of temporal modifications. If you look at the energy of the rolls as a function of time, they take a long time to begin to decrease. It's essentially constant for what we call the first stage of turbulent decay. So our hope of trying to use some temporal modulation to modify the rolls was not going to work. This is what Vignesh presented earlier. The most promising thing we found is actually looking at a mixture of no-slip and free-slip boundary conditions. So Vignesh presented this. I'm not going to repeat myself, but I think this is the most promising thing we looked at. So two things we're actually studying right now, modifying the rolls. Well, we now take the opposite thing. Can we actually incite or generate rolls by these roughness or no-slip patterns? There is this paper from the Twente group, Simulations and Experiments, and they actually show this. I don't think they make a big point of this, but they actually show that you can get rolls, you can induce rolls by putting in some roughness, and you also probably can control the wavelength of the rolls by putting in the correct shape of roughness. And this is something we're looking at doing using no-slip and free-slip. Rather than controlling the rolls, now we want to induce the rolls. And the other thing we're looking at is about periodic forcing. So there's this paper by Verschhoff et al., and they found some interesting properties depending on how you modulate the inner cylinder of, they're basically forcing with only the inner cylinder, and they start modulating the cylinder rotation. And something they found is that, you know, you have several patterns depending on if your modulation is small and large. And what we're finding is that the crucial parameter that splits a few regimes is basically dependent on the friction velocity. And if you look at things from the point of view of the friction velocity rather than the Wormsley number, you can actually start to learn some things about this. And going back to Michael's point about this being very similar to the Stokes problem, we're actually deriving some similar relationships to the Stokes problem using Taylor-Couette. So maybe a few wrap-up thoughts. I mean, for me, the most interesting thing still seems to be the roles. We're working with some computers, graphics people on how to isolate them. Maybe, how to isolate them across parameter space. Maybe we can learn how to manipulate them. And I have the feeling that this will teach us, still has to teach us a lot about shear turbulence. Studying how roles interact with non-standard boundary conditions or fluids, you put a polymer in, you put compressible, you put maybe non-Newtonian, seems to be a very promising research avenue. We don't really have the equipment to do it, and we don't really have a lab, even if we have some small things going on. But this really seems like something you could spend years researching if you wanted to. And then there's the final point of, high curvature Taylor-Couette is completely unexplored. Simulation and experiments are very hard. I wasn't aware that Cottbus people were doing it until this morning, but we tried to do simulations at radius ratio of 0.1, and we found it really, really hard to do a lot of things we found it very hard to get to high Reynolds number. And that's about it. Thanks for listening. And here's a picture of actually an experiment we're doing in Texas. And with this, Taylor-Couette comes back to Texas after the original, Sweeney papers in the University of Austin. So I'll leave it here and take any questions.
Thanks, Rodolfo, for this very nice talk. Also combining several topics that we had today, with the oscillating and with the riblets and other topics. Are there any questions from the audience by raise your hand or type or speak up?
Well, I can ask a question. So I don't know how you do this. So I have a question on these rolls. I mean, on the one hand, there's rolls, there's a bulk flow, and you argue the bulk flow is the most important thing. On the other hand, there are boundary layers, and yes, there's both. And in fact, the flux through any cylinder is conserved, right? I mean, anything what's happening in the boundary layer is reflected in the bulk, and anything which is happening in the bulk is, of course, reflected in the boundary layer. They're intimately coupled, and so that's I think it's too simplistic to say it's only the rolls which are responsible, because the rolls, they cause some shear in the boundary layer, and both is intimately coupled. I mean, it's a very nice talk, Rodolfo. I mean, so it's very nice.
Yeah,
but I think it's too simplistic to say it's only rolls. It's always both.
What I don't really understand, what I'm saying is that what happens in the boundary layer seems to be not that important for generating these kind of fixed structures, because you're also able to generate them with these Walef flow boundary layers. Something I've been trying to do for a while, but I've never been able to actually run, is the homogeneous shear flow that has absolutely no walls. And you also have large-scale structures there. I'm really interested to see how the rotation affects these, but they have not yet been able to simulate this, because this is a really, really hard problem to simulate.
But it's simply that of course, for the structures, I mean, the roles determine it. But it is if you take any cylinder, any coaxial cylinder, the flux, the Nusselt omega, through any of these cylinders is the same. It's simply conserved, right? So I think one must, by totally separating it in either rolls or boundary layer, it's kind of dangerous, because they are intimately coupled.
My point was that the boundary layers seem to not be the determining factor in generating the rolls, not that the boundary layer does not play an effect.
I see. Well, I mean, on that I fully agree. Yeah.
Are there more questions for Rodolfo?
I had a small this thing. I could not understand the part where he said how the roles are physical with respect to the. I mean, I could you please repeat that? I kind of missed.
Yes, I'm sorry. So the idea is that for a long time we had an argument that sometimes when your simulation domain, you have a periodic simulation. When it's very small, you generate unnatural things, right? But the problem is, you know, if you make it twice as large, it's not secure. I mean, it's telling you, you know, if you make something twice as large and you stop seeing something, you know it doesn't exist. But if you make it twice as large and you stop and you still see the same, it doesn't tell you that if you make it twice as large, you will not stop seeing it. So the only real way we could actually show this is by showing that the rolls have a constant energy regardless of the size of this.
Okay, thanks.
All right, perhaps one last final question for Rodolfo, anyone? Or in the chat, or raise your hand or speak up. That is not the case. Thanks again, Rodolfo.
Thank you.
And thanks everyone for attending, of course, today. So this was the last talk for today. Tomorrow the schedule will be very similar to today, so the same end and begin and end time. It will be the same video link, so it's very easy to find. And we hope to see you tomorrow. Laurette and Sebastian, anything to add?
Yes, a few things. One, several people have asked about recordings. You know that the sessions are being recorded, and I know that many of you are very eager to see them, these recordings. So Sandra will tell us where the recordings will be.
Yes, I don't know yet. So we are recording, but I'm not sure where the recordings, how they're saved and things like that. So once I figure it out, we will probably upload them to YouTube somewhere. We have an ICTW account for this year, let's say, and then they will show up there. Yeah.
Okay. And we'll put that on the website when they're there or something.
Once they're there, we will put them on the website. Indeed.
Well, okay.
Yes.
And secondly, maybe you're not aware of this, but I know many questions were asked in the chat. You can save a copy of the chat. There's some buttons to do that. I know the chat disappears at the end of the Zoom, but the 3 buttons, I believe, allow you, yes, the first, if you press on the 3 buttons at the bottom, there's a thing of save chat, and then you could save the chat, and then your questions won't all disappear. And that was my second comment. And the third comment was a reminder that we'll put the ad on a little later, that Rich Leptov is seeking people who would write articles for a special issue of Philosophical Transactions in 2023, and we'll put that up next time. And was there anything else, I wonder?
I think that was it. I hope you all enjoyed the first day, and then we hope to see you the next 4 days as well. We had a good amount of people joining, between 80 and 100, so it was very nice. I think that's already by itself a record, I think, if you discount the people that were sleeping when there was an original ICTW. So thanks all for joining, and we hope to see you tomorrow as well. Thanks.
Okay.
Thanks.
Sebastian, you can stop the recording.